In today's lesson, we're going to be taking a look at numeric variables, and in particular, we're going to be discussing three things: what numeric variables are, how they can be declared, and how they can be used to perform useful computations. So let's get going. As a motivating example, let us look at the same expression that we looked at last time around. Most of the details in this expression are not interesting for us. The only thing to observe is that 3.14159 written into the argument of the sine function. Now, this number is clearly supposed to be the number pi, or rather an approximation thereof, and that is fine. If we want to do this, we do not actually have to type it out because R already has a built-in symbol, spelled pi, for pi, that represents the same value with many more decimal precision. So it is actually preferred that we use that built-in symbol instead of typing out the number ourselves. Again, the symbol pi, represents the number pi with many decimal precision. Warning, as I mentioned last time, computers can never represent numbers with infinite precision, and that means that while pi is stored with many decimal precision internally in the computer, it is not infinitely precise, and that can lead to results that might seem weird at first sight. For example, if we want to compute the sine of the number pi, we know from mathematics that that is supposed to be exactly 0, but if we try to compute it, the computer will actually return 1.22 times 10 to the minus 16th. In other words, a number that's very close to 0, but not quite 0. Such artifacts can happen when doing computations, and that is just something we need to learn to live with. Anyway, leaving that point aside, the important idea here is that we can use a symbol such as pi to represent a number. And that is the important idea that we're going to be exploring here, because we can define our own so-called variables, that is, symbols that represent particular values. And here on the screen you can see one example of doing so. I'm defining the symbol x to stand for the number 9. And the way you have to do this in R is you first write down the symbol's name, which I just call x in this case. Then you write down this funny arrow symbol, which consists of a less than symbol and a dash. And then you write down the number that you want your symbol to represent. In this case, I just picked the number 9. So in a way, the way you would read this is that the number 9 is fed into the symbol x, and that is represented by this arrow pointing towards the symbol x. Okay, so if you run this line in R, then from that point on, x will stand for the number 9. So for example, if I want to compute the square root of x, then the way this will be interpreted is that first, the symbol x will be replaced by the value that it represents. So square root x will translate into square root of 9, and that of course evaluates to 3, which is exactly the result that we get. What names can we give our variables? It turns out that we have a lot of freedom in giving them names, but there are a few rules to observe. The most important one is that only letters, numbers, the period, and the underscore can comprise the name of a variable. So no spaces, no dollar symbols, no other special characters. Forget about that. It has to be letters, numbers, period, and underscore only. The second rule is that the name has to start with a letter. Technically, I mentioned this only in parentheses, the name can start with a period as well. However, such variables do tend to have a special meaning in R, so my recommendation is that while you are only learning to work with the R system, if you're a beginner, then just stay away from that. Easiest method is just to start every variable name with a letter. And finally, R has a bunch of built-in reserved words that are used for a very particular purpose, and many of them we will be learning about in this course. Some examples are listed at the bottom of this slide. For example, the word function has a very specific purpose in R, and the word true and false and if and so on and so forth. These have special meanings to R, so they are reserved and they cannot be used as variable names. You can get a full list of what are the reserved names by typing in a question mark and then the word reserved, as you can see on the slide. If you do that, you'll get the whole list of what are the reserved words. There's no point in memorizing this. R will tell you if you are trying to assign a variable to a reserved word. So that is not really a problem. Just be aware that this can be an issue. So to give an example of how these rules are applied in practice, here we have a bunch of valid and also invalid names, and let's just check why they are valid or invalid. The first example says first underscore result, and we assign to that variable the number 42. This is perfectly valid. It consists of only letters and the underscore. Those are allowed, and the first character is a letter, so nothing wrong here. The second example, first dot result, is also perfectly valid because the name consists of only letters and the period. Again, those are allowed, so this is all correct, and the first character is a letter, so there's nothing wrong. The third example, on the other hand, is incorrect, and the reason is that it starts with a number. Otherwise, it is a correct name. Were it not for the fact that it starts with the number 1, that is not allowed, so you cannot do this. That is an invalid name. The fourth example on the screen, first result, is invalid because it contains a space, and the space is neither a character, meaning a letter, my apologies, nor a number, nor yet a period, nor yet an underscore, so that is not a valid name. Spaces cannot be part of variable names. Finally, there's a variable name called break at the end, and that looks perfectly fine. And you might be wondering why this breaks down, because this is in fact invalid. And the reason it is invalid is that break is one of those keywords, reserved words, that cannot be assigned a value, because they're reserved for a different purpose in R. So that is why that is an invalid name. Incidentally, in case you're interested, you can override any of the naming rules if you enclose your variable names in backward tick marks. And I have to emphasize, these are those silly looking backward ticks, not the forward quote marks, the single quotes. So it's not those, it's the backward tick marks. If you enclose your variable names in the backward tick marks, then it turns out you can give absolutely any name to your variables. So here is a simple little example. We can define a variable called crowns to dollars, and that is an invalid name, or rather would be without the backward tick marks. The reason is that it has spaces and it has the dollar symbol, so that would not fly, but since we include them inside the backward tick marks, it is actually perfectly valid. So this is supposed to store the approximate exchange rate between Swedish crowns and US dollars, about 0.09. So we assign it the value of 0.09. Then we define another variable called my money, parentheses SEK, that is Swedish crowns. Again, this variable name would not be valid because it has spaces, it has parentheses, all sorts of non-standard symbols, but it is valid now because of the backward tick marks. And let's say that we have a whopping total of 137 crowns on our account. So we assign the variable my money SEK 137. And if we want to convert this number into US dollars, we can do that. We again define another variable called my money US dollars. Again, this variable name would not be valid without the backward tick marks because of the spaces and the parentheses, but this way it is valid. And then we assign it the value of the product of my money in dollars times the exchange rate between crowns and US dollars. And if we do that, then we can get back the value of my money in US dollars. And if we do that, then we get back the result that it is 12.33 US dollars. So this example was supposed to have shown how you can override the usual variable naming conventions or rules rather, using these backward tick marks. Now, I'm not going to rely on that a lot in this course, just showing you that if I were to write a program like the one in the bottom box, then I would do it in this way, giving it names that are syntactic, that do not require the backward tick marks. But it is good to know about the option if that's there. And also, if you're taking this course at Linköping University, then if you want to, for example, include Swedish characters in your names, those would not be allowed without the backward tick marks. So it is good to be aware of this option. Now imagine that my fortune really rises in the world and I get more money and my fortune increases to 200 total crowns. Can I just overwrite the variable my money sec and assign it the value 200? You might be wondering whether this is possible because we've already assigned a value to the symbol, and you might be worried that it is not possible to overwrite those, but in fact it is possible to overwrite variables. It's always the last assignment that's valid. So if we had my money sec equal to 137, but then we decide, I want to set it to 200, you can just do that. You say my money sec arrow 200, and that will assign the value 200 to the variable my money sec, and the computer will forget the previous value and overwrite it with the new one. A slightly trickier question is what happens to my money US dollars? After all, when we defined my money US dollars, it was defined in terms of my money sec, right? It is the product of my money sec and the exchange rate. And since we have just changed my money sec, does that mean that my money US dollar also gets automatically changed? And this is a very important point to remember. It does not. It does not get automatically updated. We have to rerun that line and recalculate the value of my money US dollars. So that's important to keep in mind. And it also foreshadows a theme, namely that it can be a bit dangerous to reassign variables because it can have unintended side effects like this. In this course, therefore, I will be emphasizing a style of programming that relies on reassignment of variables as little as possible. And you'll see what I mean by that as we go along with the course. To showcase what variables can be good for, let us look at a slightly more complicated example, one that is both more complicated but also more useful in the real world. And what we're going to be looking at is distances between points on a sphere. So for example, if we want to calculate the distance between two cities on the globe, such as the distance between New York and London, then we can try to find that shortest distance between the 2 points. And we assume that the 2 points are given by a pair of coordinates, which are given as latitude and longitude. So you can see on this little graphic that we have 2 points, x1, y1, that is a point with latitude x1 and longitude y1, and another point with latitude x2 and longitude y2. And we want to find the shortest distance in between these 2 points. Now, if you've never seen the formula that expresses this, and you're not used to longer formulas, you might be slightly scared. This is what the formula looks like. I'm going to explain what the symbols mean in a moment, but just that you know, this formula is the so-called haversine formula, and this gives the distance, the shortest distance between 2 points on a sphere. So in this formula, the distance is denoted by d. Little r denotes the radius of the sphere. And then we have a bunch of other symbols. A sin simply refers to the arc sine, so the inverse of the sine function. And then within the argument of the arc sine, we have a square root, and in the square root we have the squared sine of the difference of the latitudes halved, plus various other combinations of squared sines of differences between latitudes and longitudes, and sometimes there's some as well. It doesn't really matter what the details of this formula are. If you're not used to this kind of formula, it can look truly horrendous. But the point is, for the computer, it is just as simple as any other formula. And in fact, let us show how we can implement this haversine formula in R so that we can compute the distance between any 2 points on a sphere, such as 2 cities on the globe. So to aid with that, I've included the coordinates of New York and London here. Approximate coordinates, I rounded them a little bit just to have nicer numbers. And you see that in the first 2 columns, we have the latitudes and longitudes expressed in degrees. But then, since the functions in R take radians instead of degrees for the trigonometric functions, I've also converted these degrees into radians. So you have the latitude in radians and the longitude in radians for both New York and London. And the other thing to know is that the radius of the planet Earth is approximately 6,360 kilometers. Yes, Earth is not in fact a perfect sphere, but it is a good enough approximation for most practical purposes. Most certainly for this particular example. So what do we do now? We actually implement the Haversine formula in R. And the sort of naive approach would be to just do that directly. We substitute in all the numbers from this table and the radius as given above into the formula, we type it out, and then we end up with this giant formula and end up with the answer, which is 5,630.614 kilometers. Incidentally, this value, despite all the roundings and the fact that the Earth is not a perfect sphere, etc., this number is within 1% of the true value of the distance between New York and London, so this formula is quite useful. Notice also that the formula is so long that I had to enter it on 2 lines so that you can see it. Now, you may type it in R in a single line, that's fine, but you can also break the line, and that will be perfectly legal as well, as long as the end of the line indicates that the expression is not quite finished. In this case, for example, the line ends with a minus symbol, which means something must be subtracted, so R will know automatically that the expression is to be continued. So as long as that is true, R will understand this. You can break up expressions across various lines, multiple lines, and you can run them, and it will be run as one whole expression. Now, I said that this is a bit of a naive approach of doing things, and why is that? Well, it's because it's very, very easy to make a mistake when we enter a formula using this mess. In fact, I have a confession to make. I made a mistake when I entered this formula, and I wasn't trying to, but it still happened, and I knew that because I got a result that wasn't reasonable. So then I had to check, and then I noticed that I messed up something in the formula, and then I fixed it, and then it was correct. So what can we do to sort of help ourselves a little bit, to be able to write down this expression in a way that is not so error-prone and a bit more interpretable, a bit more readable for other humans? Well, what we can do is to notice that this formula has quite a bit of regularities in it. In particular, the expression of the squared sine appears 4 times in 4 different places in this expression. Moreover, 2 of those are identical, right? We have the squared sine of x2 minus x1 over 2 times in this formula. That means that if we would define new quantities called h1, h2, and h3, and they would be defined as these squared sine quantities, then we could rewrite the above formula, the Haversine formula, in a much simpler way. It would simply become 2 times the radius times the arcsine of square root of h1 plus 1 minus h1 minus h2, and that whole thing times h3. And that would be much more convenient to implement. And in fact, we can do that by defining variables. Let us define the variables h1, h2, and h3, and they will be computed exactly the way as we see in the mathematical formulas above. We just substitute in the particular latitudes and longitudes that belong to, in this case, New York and London. And we do that, we define the variables h1, h2, and h3. And if after having done that, then the Haversine formula becomes much, much more pleasant than it was before to enter. We do that, we substitute in the radius of 6,360 kilometers, and then we evaluate the final expression, and we get the result, which is exactly the same as before, as it should be. So this solution is quite a bit better than the previous one, of course, much more clear, but it's still not perfect. In particular, the latitudes and longitudes are represented by numbers, and it's not obvious which number refers to which latitude and which longitude, and if you're a human and not a machine, then it's very easy to get lost in that. So even better would be to define a couple of more variables. Let's call them lat1, lon1, lat2, and lon2 for the latitudes and longitudes of point 1 and point 2. And if we do that, we can rewrite the whole haversine formula in terms of those latitudes and longitudes. Notice now that the definitions of H1, H2, and H3 happen in terms of those symbolically defined latitudes and longitudes, and this is much more clear now than it was before. And this short 7-line program, if you think about it, not only computes the distance between New York and London, it can be very easily modified to compute the distance between any 2 points on the planet. And all one needs to do is change the data in the first 4 lines, change the latitude and longitude data, and then rerun the whole program, and then we will get back the result for the distance between those 2 points. So with that, we've reached the end of this lesson, and feel free to give yourself a pat on the back, because we finished by writing a fully fledged R program that computes something useful in the world and something quite non-trivial. So that's it for today, and I will see you around next time.